My name is Rick Branson. I'm an architect of data stacks, and I want to talk about solid state drives. How many of you guys have solid state drives in your system? You guys are lucky. See, look at these Walmart guys love solid state. How many of you guys are playing with or are about to roll out solid state into your infrastructure? One of our sales guys is back there. You go talk to this guy afterwards. So I know, how many of you are actually have Cassandra on solid state? Okay, so yeah, so we know who's lucky in this room. So it is kind of a fact that Cassandra's storage engine was optimized for spinning disks. And this system is called LSM trees, for log structured merge trees. I'm going to talk about a little bit about the write path. I'm not going to talk about everything with these because they're kind of complex. So I'm just going to talk about the write path to kind of illustrate some reasons why Cassandra and SSDs are such a good match. So when we write to Cassandra, we send a little insert here, which may not be the highest contrast up there, but we're just kind of doing a simple insert here. And Cassandra writes this to an on-disk commit log, as well as in memory in this thing called a mem table. So this kind of happens in sequence. And the mem table is kind of a materialized representation of what's in the commit log. And then we do this thing called a flush, where we take that data that's in the mem table, and we just sort of flush it to disk as it is in memory. And it's in this sorted order. So then, as was talked about before, we have to do this compaction process to maintain read performance. So, instead of having to go through all of these different tables, we just can check one instead, and we actually merge these together into a larger. So we take 4 tables, we do some conflict resolution, and we actually can get better performance by merging these together. So the takeaways for this are that all writes in Cassandra are sequential append-only operations. Cassandra does no writes as random I/O. And these on-disk tables are written in sorted order, so merging them together for compaction is a very fast linear complexity operation. And this also has this interesting attribute where SS tables are actually immutable. So once they've been written to disk and fleshed out, we know they'll never be modified again. And this has some interesting properties. So this is really important. So if you remember anything, this is the important thing. So comparatively, most popular data storage engines use B trees and use systems that rewrite modified data in place. So they go out when they're doing a change, when they're doing a modification, they actually go to the data where it sits and they modify it. And so they do a little bit of buffering like we do with our mem tables before it actually gets written out, but it's still random. It's still going to be random. They can try to kind of polish it, but it's still there. So spinning disks, let's talk about a little bit about spinning disks. So we talked a little bit about it before. I'm going to refresh your memory. They are dirt cheap. They're about 8 cents a gigabyte now, which is ridiculous. But their seek time is extremely limited. So it's like just waiting for this thing to spin around until it gets to the data point. So, and it's basically been this way for a very long time. 7200 RPM drive, 120 I/O operations per second. 15,000 RPMs is the fastest spinning disk you can get. It's been the max for decades now. They're all right at sequential operations, though. So if you can stream data from the disk in order, you get about 125 megabytes a second on a modern sort of 7200 RPM commodity drive. And that was the world in which Cassandra was built. So let's talk about 2012. We've now got this stuff called MLC NAND flash, which is really cheap, big flash drives. So now, in 2012, we're about $1.75 a gigabyte for MLC NAND flash. We can do about 40,000 reads per second versus 120. So you can imagine that makes a pretty big difference. Write performance, not quite as good. This is an Intel 320, which is the newer generation of Intel's commodity drives, 23,000 writes a second. And our latency is just minuscule compared to the 10 milliseconds that we're waiting around for a spinning disk. We also get, these days, it used to be that SSDs had poor sequential I/O performance. Now they are actually quite good. This is a $500 drive with 300 gigabytes of space, and we're doing 270 megabytes a second reads and 205 megabytes a second writes. As said before, The real important thing here is that our IOPS are 2 cents an IOPS versus $1.25. That is the most important thing when you talk about databases. But we often get this question asked, with random access storage, where you can just kind of go wherever you want, is all this work to do this sequential writes in Cassandra just obsolete? Well, as you might imagine, my answer is going to be no. Because solid state has some major problems. There are some real caveats with solid state drives. You can't override solid state drives directly. So when you actually do an overwrite, when you modify data on a solid state drive, you have to erase it first and then rewrite it. So that's not too bad. But then we can only write in small increments. We can write in 4 kilobyte, we can write and read in 4 kilobyte increments, but we can only erase in these huge erase blocks, which are like half of a megabyte. So that's kind of odd. Still not too bad. Then we run into our latency problem. So we can read and write at this, very, very fast, low latency speed, but then we hit erasures that are like 2 milliseconds, which doesn't seem that bad, but when you're talking about, basically a 1/100th of the performance, it's kind of a drag. But the real killer with this is the durability. So if you want to get really good performance for a low price, you need to use MLC SSDs. And you get about 5,000 erase cycles out of each block. And that's not a lot. You can really quickly wear through that. So what they've done is they've come up with this thing called wear leveling. So this is built into the controller, and it's designed to reduce the number of total erase operations. And it kind of looks like this. So imagine this grid here is an SSD, and each of these little tiles here is an erase block. And then we blow this up, and we end up with a disk page. So that's the kind of the 4 kilobyte guy. Now this is not the scale, but you get the idea. The disk page is what we can read and write, but this whole block is what we have to erase. So when we do a write, it kind of looks like this. We have a write come in, then we have another write come in that's a little bit smaller, and then we have the third write come in that fills the rest of the block up. So if the whole block must be erased, how is data from only write to modified? How do we do that? Well, what we do is we actually just mark that as garbage. So we take what was there, and we have a separate area that we have a garbage store. We collect the data, we basically collect information about the drive, and we mark that region as garbage. And the controller does this. And then we find an empty block or a partially empty block, and we append the modified data there. And there's a mapping that the drive does to kind of redirect all the writes to this new area. So I know that word garbage is standing out to you guys. So it's like garbage. Well, that means fragmentation, which means garbage collection, which anybody who's ever dealt with a garbage collector knows they're not the fun guy at the party. So what does a garbage collector do? And I think garbage collection was mentioned earlier. It compacts fragmented disk blocks. So it takes those empty spaces between the writes, and it merges them together. Unfortunately, though, some of these erase operations drag on performance, and so do some of the reads and writes. So this garbage collection process actually does drag on performance a bit. And modern SSDs do this as much as possible in the background. So like a well-behaved SSD does this in the background as much as possible. But if there are no empty blocks available, there's no space essentially, it has to be done before a write can take place. So then we hit that wall where the performance drops off. And then we get this thing, because of this garbage collection, we get this thing called write amplification. And this is when only a few kilobytes are needed to be written, only when you send a few kilobytes of data to the drive or a few bytes of data to the drive. But fragmentation causes that whole half megabyte block to be rewritten. And the smaller and more random your writes get, the worse this gets. It's pretty bad. And the garbage collection process can stem that tide, but it can't really completely eliminate it. So what does this look like? So this is a torture test that Anantech ran on a drive where they basically intentionally fragmented it. So this is a very poorly performing drive, and you can see the write performance drops from about 250 megabytes per second to like 10. And it doesn't recover. So this whole process, they're actually rewriting the entire drive to the end. So that's a 250 gigabyte drive, and they're rewriting the whole thing, and they still, at the very end, only end up with about 50 megabytes, maybe a little over 50 megabytes a second worth of write performance from where we were at 250 before. Some poorly behaving drives get even worse. So this is an OCC drive, so you can't even see where it started on this, and it barely gets any better. And so even well-behaved drives, so this is one of my favorite drives. This is an Intel 320, which is kind of the newer generation of the X25. Even a well-behaved drive suffers from this problem. So as you might imagine, a production system would not do too well if your writes look like this. Your latencies would go up and down, and you'd have problems. And this is what happens when they kind of fix it. So what they did after that test is they just marked the entire SSD as basically empty, and then voila, our performance was back to normal. So some of you guys that know a little bit about SSDs are going to say, okay, whatever. Tell me about how it works with this trim stuff. So trim is this command, and file systems don't actually erase data when you delete a file. They just mark it as deleted, and they kind of have processes that come back in later, and they do kind of, everybody's doing garbage collection. But trim basically allows the OS and the file system just to say, in a very lightweight manner, that this region of the disk is no longer used. So instead of having to go through this expensive erase process, which causes like a spinning disk, for instance, to actually erase the data, a trim is just sort of a hint that says, hey, I no longer need this data. So if the entire erase block is marked as unused, then we can avoid that garbage collection compaction process because there's no fragmentation. Otherwise, the trim will just sort of speed it up and make it a little bit faster. Trim can only reduce the effect of write amplification. It can't eliminate it. And the other thing is, then there's lifetime. So how long will my SSDs last if I'm just pounding them with a database kind of load where I'm doing lots and lots of random writes? And I have a high level of write amplification. So Anantech did a little measurement, and they found that on a modern MLC SSD drive, like an Intel 320, they last about a year and a half under like a heavy MySQL load, which causes around 10x write amplification. That's pretty bad. You spend $500 on a drive, you might put 8 of them in your machine, and a year and a half later, you start losing them. Before the machine's halfway through the lifetime of the average machine in a data center. So what to take from this? Remember this? I said all disk writes in Cassandra are sequential append-only operations. So Cassandra only writes data sequentially. From a paper put out by IBM Research, and this is, I'll leave you with this. For a sequential write workload, write amplification is equal to 1, as in there is no write amplification. Thank you.